So this week I'm very pleased to present Sun Kwok. So Sun is an old-time friend of many of us who was a long-time faculty member in Calgary and spent many years in Hong Kong in sort of university administration. He's retired back to Canada, where he's a member of their Earth, Ocean, and Atmospheric Science Department at UBC. He's an expert in many areas of astronomy. And recently, when these claims of life on Venus came out, I know Sun had many conversations with me, but probably also with many other people, because he was particularly interested in these claims and the sort of sociology of the whole thing of trying to claim life elsewhere and so on. So when we were discussing ideas for Colloquia, we thought it would be great if Sun could lead a sort of informal discussion, and he agreed to do that. So we're very happy to be able to present today the search for biomarkers in the solar system and beyond. So it's all yours, Sun.
Oh, thank you very much, Douglas. If you can't hear me okay, or you have any questions, please feel free to interrupt at any time. So the way I plan this talk is going to have, I'm thinking to have three components. The first, I'll talk a little bit about history, how people in the past thought about search for life in the solar system. Then I'll move to the present, what kind of biomarkers people are using or thinking to use in next generation telescopes. And in the end, I'll do a little bit of my own opinion on what are the assumptions being involved in the present search strategies, and a little bit of my own perspective on the whole biomarker and search of life phenomenon. So let's see. So let's start with a little bit of history. Now, the whole idea of search for life in the solar system started, of course, after Copernicus, because he was the one who determined that the Earth is just like the other 5 planets, and the daily rotation of the star is not because the celestial sphere is rotating, but because the Earth is self-spinning. So soon after that, Dix in England, of course, extrapolate this to mean that since the celestial sphere is not rotating, there's no need for all the stars to be on the surface of the celestial sphere, and therefore stars can be at any distance. So Bruno pushed it a little bit further and speculated the stars actually could be distant suns, and if they are like our own solar system, then all these stars could also have their own planets. And actually, right after the telescope observations of Galileo, where one of the first things he looked at was the moon, we saw features on the moon, Kepler was very excited. He thought that those circular craters, which we now know to be craters on the moon, are artificial constructions of people on the moon. So now this became a very common belief, actually. By the 17th century, there is a lot of speculations on populations on the moon and in other parts of the solar system. And of course, the greatest astronomer, William Herschel, was a firm believer of life on the moon. He actually wrote that the most absolute certainty of the moon being inhabited. And he, like Kepler, considered the features on the moon that he could see in his own telescope observations are the works or architecture of lunar people, and they may be their towns or infrastructure or buildings or whatever. So actually, by the 19th century, it became very fashionable for the astronomy community to believe that there are widespread presence of intellectual beings, intelligent beings in the solar system, not just on the moon, but also on Mars and other planets. Now, in 1835, at that time, the New York Sun was the largest circulating newspaper in the world. It published a series of articles about supposedly the observations of ring creatures with rings on the moon, and these reported were widely republished all over Europe and was taken quite seriously. New York Times, for example, said that discoveries are probably probable and possible, and the New Yorker said this is the beginning of a new era in astronomy and science generally. So the public is definitely extremely fascinated about the possibility of extraterrestrial life. And of course, press sensationalism has always been asked because they basically reflects or motivates what the public would like to believe. Now, of course, most of us are well familiar with the problem of the claim of canals on Mars, and Lowell was extremely popular and well known for his discoveries of canals on Mars, and in the early 20th century, he was a very popular speaker, speaking all over the United States. He wrote a number of books about the canals on Mars, and he got all kinds of honors, both in Europe and in the US, for making this discovery. Now, of course, we now know that these features are not artificial now with spacecrafts, in particular, beginning in the late 1970s, 60s and 70s. We have the Mariner satellites. Some of them are including Orbiter that had a very close look at the surface of Mars. And of course, we know that these are all geological features and not anything of artificial nature. Now, the observations that one can make is that every generation has its own set of beliefs guided by what could be observed and what kind of technology they had at that time. Now, certainly Kepler and Herschel are all very smart people, and the reason they believed that they were people on the moon was not because they were stupid, but it's just that because of the limitation of what they could observe at that time. Now, even into the 1950s, there were a lot of interest in, and maybe not animals, but at least plants and vegetation on Mars, because one can see seasonal variations of the dark regions of Mars. They go through cycles, and one of the possible explanations is that these are seasonal changes of vegetation in response to the temperature variation on Mars. And in order to have a test on this hypothesis, that when the spectroscopy was available, that it was a report in Science that using the infrared spectrometer, they could detect a feature in the near infrared, which are characteristic of plants, and that was cited as the evidence for the detection of vegetation on Mars. Now, later, it turned out that it's not really a absorption feature on the surface of Mars, but actually due to deuterium water in the Earth's atmosphere. So this claim is no longer valid. Now, of course, now we have pretty good measurements of what the spectral characteristics of different kinds of vegetation look like. So, and we should now have the capability to perform mapping of, say, Mars or other planets, that to see if there's any vegetation. Of course, there is none that we can see. So what do we look for now? I mean, there's now, of course, a lot of interest in not only the solar system, but also in extrasolar planets. And one of the things that are very of popular interest is to look of Earth-like planets. Now, the first, they have to take a look and see what the Earth is like. And the Earth actually can be quite easily observed because of Earth shine. So by looking at the new moon, one can take a spectrum of the moon and to see what the Earth's atmosphere is like. Actually, one can see the Earth spectrum, both of the ocean, of the clouds, of the continents. So we all have spectral signatures of the Earth. So, for example, you look at the clouds and you see signatures of oxygen, O2, O3, water, and so on. So these are the number of molecules that methane, for example, or N2O, are also considered to be signatures of the Earth-like planets. So one could look for those signatures in other planets, even outside of the solar system, that could be indication of life on other planets. Now, this is, of course, based on our own experience with Earth. The Earth started with an atmosphere which is very different from what we have now. Our Earth's atmosphere now has a fair amount of oxygen, and that only came after the existence of life from cyanobacteria 3.4 billion years ago, leading to the process of photosynthesis. And because of this biological presence, the amount of oxygen in the Earth's atmosphere increased significantly. So after about 2.5 billion years ago, we have a significant oxygen-rich atmosphere. So oxygen is now considered to be one of the biosignatures of life. So how do we do that? Now, is actually a very extensive plans in place for observations of the atmosphere of extrasolar planets, not only for JWST, but GMT, ELT, TMT, and so on. And there will be a European mission that will look at the atmosphere of over 1,000 extrasolar planets. And the technique is very simple. When watch the planet to be in the period of a transit, then you can see the atmosphere of the planet in the spectrum of its parent star. Now, one have to be slightly careful here, because just the detection of oxygen is not a guarantee or definite signature that is life on that planet, because although the Earth, the oxygen is primarily due to the presence of life, but in Europa, it also has oxygen atmosphere, and that we believe to be produced biologically. Now, of course, now we no longer believe there is any large animals or plants in the solar system. Mostly this is a result of spacecrafts going to observing all the planets or planetary satellites remotely, or even on the surface of the planets. And we don't think that there are any large animals or plants in the solar system. So the emphasis now is all on microorganisms. So the people are searching for evidence of life. That's what we are thinking, that we are going to look for signatures or evidence of, say, activities of bacteria. So one very commonly cited biomarker is methane. There are many reports of methane being observed on Mars, on Titan, and so on. And for the case of the Earth, there is methane in the Earth's atmosphere, and there is definitely of biological origin, mostly coming out from the gassing from cows due to bacteria in the cow's intestines and digestive system. So the picture here is some results from the Curiosity rover. It detected variation of the abundance of methane in the Martian atmosphere, and the abundance can be as high as 21 parts per billion in volume in the Martian atmosphere. So that led to a lot of coverage in the press. I mean, there are a lot of interest, not only in scientific journals, but also in the popular medium, that the methane is a very suggestive biomarker of possible microscopic life on Mars or on Titan and so on. Now let's just step back a little bit. Of course, the methane was not detected now. In fact, as soon as we are able to perform spectroscopy, first in the visible and later in the infrared. For example, I know Stephen Ridgway very well in the 70s. He performed a lot of, he has his infrared spectrometer in the 70s. He was able to detect methane and acetylene and ethane and other simple organic molecules in the various solar system objects, including Jupiter, Saturn, and so on. Now, with other missions like Galileo, Voyager, and astronomical satellite like ISO, many organic molecules have been detected in solar system objects. So this is a backdrop of saying that although we are very keen about methane on Mars, we have to keep in mind that the Mars is not the only object which has methane. Now, of course, the greatest excitement in the last couple of months has been the report of life on Venus. On September the 14th, there was a news conference by ESO reporting on the publication of a paper in Nature Astronomy and about the detection of phosphine, pH3, and that has generated a lot of press coverage. And according to the count by Nature Astronomy, which published the original article, there were almost 5,000 pieces of news reporting. So I do know for a fact, because a lot of my friends in Asia, or I got contact from newspapers or magazines in Asia when the news story broke. So there's not interest not only in North America and in Europe, but actually it's actually all over the world. And after the initial press conferences, the authors also went on to TV and radio and to promote this discovery, and that the significance is that there is not only detection of the molecule phosphine, but the possibility that phosphine is a biomarker marking the presence of bacterial life on the in the atmosphere of Venus. So let me spend a couple minutes going through the original article and talk about what actually the scientific content was. So pH3 is a symmetric rotator like ammonia. So it has rotational transitions that one can detect, although it doesn't have an inversion transition as the case of ammonia, which allow it to have centimeter wavelength transitions, but it has to be in the millimeter wavelength. So the lowest rotational transition is 1 millimeter, and the paper reported two detections, one with JCMT and another with ALMA. So a very narrow line of about 4 kilometers were detected in the upper atmosphere of Venus, and from there they derive an abundance of the molecule of 20 parts per billion. So making a note that pH3 on Earth is the result of bacteria. So they suggested from various chemical models that the detected amount of phosphine cannot be produced by various geological means. So it's the paper suggests that most likely explanation is that bacterial life in the clouds. So there were two papers which goes into more detail into the life interpretation. The original paper in Nature Astronomy was mostly about the detection of the molecule itself, but the extrapolation of being evidence of life in Venus is in two papers which are published in the journal Astrobiology. So you can see in this illustration from one of the papers is that the life is supposed to be on part of the clouds of Venus. So again, like in the case of methane, we have to put things in a little perspective because phosphine already been detected on Jupiter and on Saturn before Venus. And for example, the Cassini spacecraft and the infrared spectrometer, and the amount they detected quite a bit of phosphine. I mean, in the case of Jupiter, is 5 parts per million. So it's quite a bit larger amount, and also in Jupiter. Now in the Earth's atmosphere, it's much less. It's parts per trillion. So we don't have as much phosphine as in the case on Earth as in say Jupiter or Saturn. So this because of the very large publicity of the discovery, there were quite a bit of reaction from the scientific community. And I think the early reactions are on 3 points. So because they typically, because of line of confusion, in order for us to claim a molecular detection, we usually have to have 2 or 3 or more transitions to be sure. And some people are concerned that the authors removed the 12 order polynomial baseline from the spectrum, and because when you have such a high order polynomial, you are basically putting in more free parameters into the fitting. And there are also people who think that we cannot totally exclude the possibility of a biological origin of the molecule. Now let me illustrate what we mean by a line confusion. Now with the detectors are so good and the telescopes are so large, actually we are very good in detecting molecular lines. So in this spectrum obtained with the 12-meter telescope in Arizona, every feature that you see in this spectrum is a molecular line. There's not a little bit, no noise on this spectrum. So there are so many rotational lines in the medium part of the spectrum that actually everywhere is a line. And so for us, that's why the first comment that in order for us to be sure that we have a detection of any specific molecule, we need more than one line, and then all the multiple lines have to have the string ratio, which is similar to what we expect based on the they say, for example, molecular laboratory spectrum of the molecule. So that's the problem of line confusion. And also the molecule pH3 are also seen in the dwarf stars. So you can see in this spectrum, there are 2 lines detected, the first and second transition of the rotational transition of the molecule, the higher one being at 800 gigahertz is done on the Herschel satellite, and the lower one was done at the IRAM 30-meter telescope. So you can see that the signal to noise of these detections are very good, and so we know that in the stellar wind of evolved stars that phosphine are being made in the stellar ejecta, and the abundance is well, I mean 10 to the minus 8, which is not totally unexpected. Well, in the context that because we know that there are over 80 molecules that have been detected in the stellar wind of evolved stars, including different kinds of organic species, including methane, for example, and acetylene. So it's not totally unexpected. Now, the paper was published on September the 14th, and almost right away there was a preprint appearing, which was eventually published in October the 27th in ANA of the using the Texas spectrometer on the ILTF. And there are a number of vibrational transitions of the molecule around 10 micron, and the infrared observations were unable to confirm the detection of the molecule. So actually, the upper limit, according to the infrared data, is 5 parts per billion, which is 4 times lower than the results of the millimeter wave detection. So I just want to mention that 3 of the authors of the original Nature Astronomy paper are also co-authors of this infrared paper. So there was another preprint which was submitted soon afterwards and eventually published in the December 1st issue of Astronomy and Astrophysics, questioning the use of the 12th order polynomial fit to in the original detection. So the paper claims that if one used this kind of high order polynomial, there would be a number of other lines near the pH3 lines, which are probably artificial in origin and not necessarily representing actual detection of a molecule. So they concluded there is no statistically significant detection of by ALMA of the line in Venus. So there is another paper which is submitted to the Nature Astronomy as a comment, and this time the emphasis is on line contamination. So because the pH3 line is very close to a strong line of SO2, it's only 1 kilometer per second away. So, and it's very difficult to properly analyze spectroscopic data for an interferometer. So and of a source which is very bright and extended, such as Venus. So the conclusion is that well, one cannot rule out that the feature was seen is being affected by the line from SO2. So now after these papers, there were 2 responses from the original authors of the Nature Astronomy article. One was just published in AstroPH a couple of days ago. And here I try to summarize what the responses are. First of all, they stand by the JCMT observations, so they think the JCMT detection is real. However, the ALMA data, after reprocessing, then they think the detection is much weaker than originally claimed. So in order to reconcile that there is a line detected by JCMT but not anymore by ALMA, then they suggest there is a possibility of temporal variation of the line because of the time difference between JCMT and the ALMA observations. So the conclusion is that given that both ALMA and JCMT were working at the limit of the capabilities, they would like to take further spectra with other telescopes. So interesting thing is that one of the authors of the critics, the author in Apology, later not so much on the science, but on the language they use in the criticism of the paper. Now, in September the 25th, which is about a week after the news announcement of the Venus on Life announcement, there was a statement from the French Astrobiology Society. The statement is very long. I don't want to read it, except to say that they say that, or to remind everyone, there is the responsibility of scientists in the field of astrobiology to produce observations and interpretation with the greatest scientific rigor. So there were obviously some concern in Europe, or in France in particular, about whether the claim of life on Venus is significant or not. The IU Astrobiology Commission on October the 5th also issued a statement. Now, this statement is much more milder than the one issued by the French Astrobiology Society. Basically, it was just saying that one had to be more careful talking to the press and so on. But IU received a lot of complaints as a result of this statement by the commission. So the president of IU ordered the removal of this statement and asked the commission to make an apology to the authors. Now this last couple of years, actually, is quite interesting, because the issue of biomarker is not just methane or phosphine, but actually in other more complex organics. Now, there were two papers, one in Nature and another in Science, which were also generated a lot of publicity, both published in 2018. There were quite a bit of news coverage in the press, but probably not as extensive as in the case of life on Venus. Now, what they detected was, in the case of Mars, using the Curiosity rover, that they drew samples on the surface of Mars. They have instrument analyzing the sample right on site, and they detected evidence for very complex organic compounds similar to kerogen on Earth. So similarly, in the case of Enceladus, there was also evidence from the Cassini mission that there are plumes or ejecta from the satellite that contain signatures of very complex and macromolecular organic compounds. So these were all both cases being reported, both by the scientists and also in the press, as possible signatures of life on Mars and also in Enceladus. Now, this is again based on our knowledge that kerogen is the result of life on Earth. Now, on this table, you see that among the largest reservoir of organics on Earth, or carbon compounds on Earth, is in the form of kerogen. By comparison, the biomass in the Earth's surface, including the ocean, the continent, and the atmosphere, is much, much less. So most of the Earth's crust contains a lot of evidence of life in the form of kerogen, which is a very complex organic material, which is the result of the decay of animal and plants on Earth after thermal processing over time due to pressure and temperature. So this is a chemical structure of kerogen. You can see that there are islands of aromatic rings of carbon, as well as chains of these are called aliphatic structures linking the aromatic rings together, the rings are of random orientation and sizes. This is the chemical structure of kerogen. Now, we are very fortunate that we have meteoroids. Meteoroids is very useful because we can hold them in our hands and we are able to, these are celestial material, but we can put it in the laboratory and use all kinds of techniques to analyze their content. So there are basically two components in a meteoroid. One is so-called soluble, that means you can dissolve it in acid and you can look at the compounds which are being released and you can analyze them. And tens of thousands of organic compounds have been detected in this soluble portion of meteoroids. I mean, including over 100 amino acids. Now, we have to remember on Earth, we're only using 20 amino acids for our life, living organisms. So there are other amino acids which are in meteoroids, which are not being used for biology on Earth. So basically, every biological compound that we know of are present in the carbonaceous meteoroids. And we know that these are not of biological origin because the abundance decreases with number of carbon atoms. So they are probably being built up from smaller and smaller carbon species to large ones. Now, not only there are more amino acids, on Earth we have 5 nuclear bases, but in carbonaceous meteoroid we have several more nuclear bases. That means the biochemistry that is possible is much more wider than what we actually use on Earth. Okay, now the more interesting is the insoluble compound, so-called IOM, in meteoroids. So 70% of all the organic matter is in the form of the IOM. And if you analyze the content, they are mostly made up of aromatic rings and aliphatic chains, and including other kinds of impurities like oxygen and sulfur and so on. And so these are very similar to kerogen on Earth. Now we know that because of Cassini-Huygens landing on Titan, there are lots of complex organics on Titan, both on the surface and also in the atmosphere. In fact, the amount of hydrocarbon on Titan is more than the compounds that we have organics on Earth. We know comets, both by remote or on-site observations. There are lots of organics in comets. They are no longer dirty snowballs, but they are, for example, you can see where clear there's this 3.4 micron aliphatic CH stretch feature in comets, whereas the structures are spectral signatures very similar to kerogen on Earth. Asteroids, they have colors which seem to indicate that they are covered with complex organics on the surface. Asteroids, they have this is Earth signature. I mean, these are the actual spectral signatures on an asteroid. They have similar 3.4 micron CH stretch. Oh, they are okay. We can even Pluto now, the recent mission of New Horizon spacecraft. They are the possible organic ice on Pluto. So there are lots of complex organics in the solar system. So not just that we can see on Mars or on Venus. So the question is, where do these organics come from? I mean, now I just want to spend a couple minutes talking about what I think they come from. So we know for sure that complex organic molecules are being made by evolved stars. they are being made at near vacuum conditions and over very short time scales, because we have this, because of the stellar wind, things don't hang around for very long. The dynamical time scale is shorter than 10,000 years. So everything that we see are being present in the ejecta of evolved stars are due to things that we are recently made. So although we cannot understand it, we don't have theoretical understanding on how this is possible, because the density is so low, and yet we have observational evidence that complex organics are forming, including both aromatic and aliphatic compounds. So these are pictures of protoplanetary nebulae when these signatures first appeared. We can see that these six stretch from aromatic compounds, and also six stretch from aliphatic compounds. So well, I mean, I'm promoting the idea that actually evolved star can make very complex organics, I mean, which we call Hmong, makes aromatic, aliphatic, organic compounds, and it's possible that all these stellar ejecta were sent out in the stellar medium. They were mixed up in they were deposited in the early solar system nebula, and then from which all the solar system objects are formed, including the comets and planetary satellites and so on. So just to summarize, I think we have to keep in mind that when we see signatures of organic molecules or compounds, that they could be of a biotic origin, because organics are very common in the universe. And we also shouldn't be paying too much attention to models, because we know that we don't have very good understanding of non-equilibrium chemistry, because we can see molecules and solids forming in a very low density environment over very short time scales, which we cannot explain by conventional chemistry. So it would be difficult to eliminate the abiotic origin of any astronomical signal and state for certain that this is due to biology. So in the end, probably the most definite way we can say that we are going to detect life in the solar system is to actually go there and take a look at a sample and see the direct detection of life itself in the sample. So that's all I want to say. And I want to talk a little bit about history, because the biomarkers that we are looking at now were different kind of biomarkers were used by astronomers of the previous generations, and we cannot be sure that what we call biomarkers are definitely signs of life. That's all.
Thanks, son.